So let's do our first one. Find the radius of convergence and interval of convergence of this series, power series. N equals 0 to infinity, -3 to the n, x to the n, over the square root of n plus 1. So the ones I did last time when I was trying to figure out if it converged or diverged, I said we always go with the ratio test. So let's do that. an plus 1 over an. Okay, -3 n plus 1, x to the n plus 1 over the square root. It's n plus 1, so n plus 2. And then I'm going to flip square root n plus 1 over -3 to the n, x to the n. And remember, you group up your like things, and that's when you simplify. So I see this -3 to the n plus 1, -3 to the n. I'm now going to simplify that. To be -3. And then I see this x to the n plus 1 and this x to the n. I'm going to simplify that to be an x. And then I'm left with square root of n plus 1 over square root of n plus 2. So I'm taking the absolute value here. I see that -3 is negative, so it becomes a +3. Absolute value of x, which remember you can't move x out of the absolute value because you don't know if it's positive or negative. The 3 and the x you can shift out in front because they're just like constants. Well, both of the numerator and denominator, they're both under square roots. So I can actually, I'm going to erase, I'm just going to save myself a line. I can combine them into one square root here. The square root, n plus 1 over n plus 2. And then the limit sees a square root, which is a continuous function, so the limit is just going to bypass it. It's going to go inside. Three times the absolute value of x, the square root, limit of n plus 1 over n plus 2. And I need to know what that limit is. So you can use L'Hopital's rule, but there's also a shortcut. When you have a polynomial over a polynomial, you can compare the degrees. So what's the degree of the numerator? 1. Degree of denominator? 1. So they're the same, so you take the ratio of the coefficients of the highest degree term. So in this case, it's 1 over 1. You'll get the same thing though if you use L'Hopital's rule. So this is what I get out when I calculate this limit using L'Hopital's rule, 3 times the square root of x. In order for this to converge, I need this thing to be less than the number. What number? Ratio test. I need it to be less than 1. Less than 1. So this one's a little bit different than the ones we had last time because I have this extra coefficient here, 3, which I didn't have occurring in our examples yesterday. You want to isolate the absolute value of x. How could you isolate it? Divide by 3. So I'm going to do that now. Let's divide both sides by 3. Once you've isolated the absolute value, the number that's over here is automatically your radius of convergence, 1/3. Okay. So I've isolated my absolute value. So this here, this is my radius of convergence. It's r equals 1/3. So we've done half the question. We needed to know the radius of convergence. And now I need to know the interval. If the absolute value of x is less than 1/3, that means x needs to be between negative 1/3 and positive 1/3. What we did yesterday was I had to test my endpoints of my interval to see if they converge or diverge. So I need to take these two numbers, negative 1/3, positive 1/3, and plug them in and see if my series converges or diverges. Okay, so what you need to do to find your interval of convergence, test the endpoints. So we go back to our series that we start with, power series. So I'm writing it here because it was way back. And you're going to start plugging in those two numbers, negative 1/3 and positive 1/3. So let's start with negative 1/3. It doesn't matter which one you plug in first. And I'm going to plug that in place of x. And I need to know, does this series here converge or diverge? Kind of messy, right? The numerator.
Could you combine the two terms of the numerator?
Yeah, exactly. Yep, I can combine the terms in the numerator because they both have the same exponent. And then I multiply to get 1, just like you told me.
You do like the comparison test that's going to plot down.
So once we simplify it down, what's 1 to the n? Equal to 1, always. So my series I'm considering is 1 over the square root of n plus 1. And now we need to use some test here. This has positive terms, so we can definitely use the comparison test like you told me. What would you compare this one to? 1 over root n. So use a comparison test. The one you're going to compare it with is bn, 1 over root n. We need n to be 1. It can't be 0 here. What kind of series is 1 over root n? A p series. What's my p-value?
-1.
It's just 1/2. It's in the denominator. If it was in the numerator, it would be negative. And remember, square root, we can rewrite the square root of n as n to the 1/2. So it diverges. P needs to be less than or equal to 1 to say that it diverges. Okay? And then, let's see. I think the direct comparison test will be inconclusive, so I'm just going to go ahead and use the limit comparison. You're computing the limit of an over bn. An is what I started with. And then I divide by bn, which I'm going to go ahead and flip it up. These are both under a square root, so I can combine them. And this is very similar to what we saw earlier, right? I moved the limit inside. What's the limit of the inside? N over n plus 1. It's 1. They have the same degree, so you take in the numerator and denominator, take the ratio of their coefficients. So this limit, you're going to get the square root of 1, which is 1. For the limit comparison test, I need to get a finite number that's not 0. I got a finite number that's not 0. So both series have to do the same thing. In particular, my series, which was 1 over the square root of n plus 1, diverges. So I know I'm not going to include negative 1/3 in my interval, but I still need to check if I need to include 1/3. Let x equal 1/3 and plug that in now. So I'm going to plug it in. 1/3 to the n.
We just do the same thing.
Do the same thing, right? It looks very similar. Combine them. What happens when I combine them? You'll get a negative 1. And what kind of series is this? Alternating. So anytime you see alternating, you think alternating series test. So that's the test we need to use now. Bn is 1 over the square root of n plus 1. And there are two things you have to check for an alternating series test. Do you remember what two things?
The limit needs to be equal to 0 and then it has to decrease.
Yep, decrease. So let's compare bn plus 1, bn. N plus 1 or n plus 2. And 1 over the square root of n plus 1. Cross multiply. So I can say which one of these is bigger. The square root of n plus 2 has to be bigger because the square root is an increasing function. So this establishes that my sequence is decreasing. The only other thing I need to check is that the limit of bn is 0. But it is. Okay. So we're good to go? What's my conclusion of the alternating series test?
Converges.
This one converges by alternating series test. So I need to include 1/3 in my interval. So my interval of convergence, I knew it's between -1/3 and 1/3, but I just learned that I don't include -1/3, so that's going to get a parentheses, but I do include 1/3. As you want to know, where does it converge? So this would be your interval of convergence.